Today we want to continue to look at definite integrals. Now, last time we looked at the limit of a Riemann sum, and we talked about what this Riemann sum was. We looked at the limit of this as n goes to infinity, and then we finished up with defining that as our definite integral. So let's kind of take where we left off last time. We were talking about our Riemann sum, which is this f of ck, which was the height of each rectangle, and this delta xk, which was the width of each rectangle. So we were finding the area under the curve with n subintervals or n rectangles. That's our Riemann sum. And then we looked at the limit of that Riemann sum as n goes to infinity. And we defined that that limit of that Riemann sum was I, our definite integral. Now, let me say one thing just to clarify here, just to be absolutely correct as we do this. As we talk about finding our area under a curve, understand we want an infinite number of rectangles. So theoretically, we could have something like this, x sub 0, x sub 1, x sub 2, out here to x sub n, and then I could get an infinite number of rectangles by just adding an infinite number out here, and those first two rectangles never get really, really, really small. So when we talk about n going to infinity, what we're implying, and we could get into a lot more math that explain this is really what it is, but we're not getting into it here. Really what we're doing is we're getting an infinite number of rectangles across the entire interval. So every delta xk is going to 0. Every subinterval is going to 0. So that's what we're talking about when we say x is going to infinity. Not that, part of it's going to infinity and then the other parts stay larger. We need every delta xk to go to 0. Once we did that, we talked about using our formulas for delta xk and c sub k and finding our limit of our Riemann sum for our function on our subinterval. And we did one example of that last time. So what we want to do today is we want to start off with another example. So first off, let's find our delta xk. This is b minus a, which is 5 minus 1 over n, which is 4 over n. And this one will be a little different than our last example because our a is not 0. Last time it went away. So our a is 1 plus k. My delta xk is 4 over n. So this gives me 1 plus 4k over n. Now, the limit of our Riemann sum is the limit as n goes to infinity of k equals 1 to n of f of ck times delta xk. So if we substitute in our two pieces of information, this is the limit as n goes to infinity of sigma k equals 1 to n. And then this is f of c sub k, which our f of x is x squared minus 1. So this becomes 1 plus 4k over n squared minus 1 times delta xk, which is 4 over n. From there, we need to simplify. So let's simplify this out. First thing we're going to have to do is, because we had that n squared, or that k squared, excuse me, right here, we need to FOIL this out. 1 plus 4k over n. If I FOIL that out, that's going to give me 1 plus 8k over n plus 16k squared over n squared minus 1 all over 4 over n. Now, as we simplify that, you can see the ones cancel. The next thing I'm going to have to do is I need to distribute this through. And if we simplify this, we will break this into two parts. Once we distribute that through, we will have 32k over n squared plus 64k squared over n cubed. Now, we can distribute that further. So the first sigma, I can take out a 32n squared, and I will have k equals 1 to n of k, plus 64n cubed, sigma k equals 1 to n k squared. Now we're ready for those formulas from our sigma notation. So this gives me the limit as n goes to infinity of 32n squared. Our formula for k is n squared plus n over 2, 64 over n cubed. Our formula for k squared was 2n cubed plus 3n squared plus n all over 6. Now, as the limit as n goes to infinity, this is 32 over 2, which is just 16. This gives me 64 times 2, which is 128 over 6. And if I simplify that, that converts to a fraction of 112 over 3, and that gives me 37.333. So there is what our integral is. The limit from the integral from 1 to 5 of x squared minus 1 dx is equal to 37.333. Now, understand, what are we doing when we solve an integral? If we have the integral from 0 to 2 of x plus 1, we could do our whole limit of our Riemann sum. But in this case, because it's just a straight line, x plus 1, we have a y-intercept of 1. Our slope is 1, so we get this line. If we're looking at the integral from 0 to 2, what we are looking at is the area underneath the curve. So we are looking at that area. Now, because this is a straight line, we can just use our area formulas that we know from geometry. And you can see I could break this up into a rectangle with a height of 1, a width of 2, which is just 2. Plus, this is a triangle with a width of 2, a height of 2 is 4, divide by 2, that gives me 2. And so the area underneath the curve, the integral from 0 to 2 of x plus 1 dx, is equal to 4. Now, the last example, that's harder to do because we have a parabola. As we looked at before, when you have a parabola, you can't just use your area formulas. But some of the problems in the homework tonight, you can just use an area formula. Let's look at another one. 2 minus x, 0 to 4. So that is, our y-intercept is 2. Our slope is negative 1, so we go this way. This way. We have the integral from 0 to 4. So the area between the curve and the x-axis from 0 to 4 is this triangle and this triangle. So let's find our area. The first one, a width of 2, a height of 2, divide by 2, that equals 2. Plus the second one also has a width of 2 and a height, but now our height goes down. What that means is this area is below the x-axis. And anytime we have an area below the x-axis, it has to be a negative 2. So the integral from 0 to 4 here is actually 0. The area above the x-axis is 2. The area below the x-axis is negative 2. Anytime you have area above the x-axis, that's positive. Anytime you have an area below the x-axis, that is negative. Now, in this case, they're equal, so it gives you 0. It's possible they're not equal, so you can get a positive or negative answer. But the thing to remember is anything below is going to be negative. Now, when you think about our limit of our Riemann sum, it automatically takes care of that because when we look at our functional value, if our functional value is negative, it will work out. So we don't need to change anything to figure that out. It just automatically comes out in the wash as we do a problem because this area, the functional values down there are negative. Now, here's an example of one we want to kind of figure out the formula for when it's just C. So if we kind of draw a picture to understand what's going on, here is C, that's just some constant value. And we want to find the integral from A to B. So if we draw this, this basically becomes a rectangle. So the height of that rectangle is just C, and then the width of that rectangle is just B minus A. You're going to do one similar to this on your homework when you want to find what's the integral from A to B of x, and you're going to do the same type of thing. You're going to have an A and a B in your answer. The last thing I want to look at is how we can do this on our calculator. So if you have a calculator, you want to pull it out. Now, some of the older calculators, this works a little differently, so if it doesn't work right on yours, you may have to grab one of my newer ones. And we're going to go to Math, just like where the fraction button is, or our probabilities and all that kind of stuff. And we're going to go down here to number 9, Function Integrator. Now, we use this a little bit as we go forward, not a lot. It's similar to using the derivative button that was also here on the calculator, which once we got into it, we didn't use a lot, but it's good to kind of help us understand what we're doing right at the start. So if we go down here to 9, to Function Integrator, it's going to bring up something that looks like an integral. And you're going to plug in your 1 and your 5. In the parentheses, you do x squared minus 1, and then you type dx. And when you do that, the calculator is going to give you 37.333. This is the calculator's way of doing an integral numerically. The calculator's basically doing the RAM rule. Much more complicated, much more exact than our simple RAM rule. It's a much better program, but that's basically what it's doing. Just like when we did, the root button on your calculator, it was basically doing Newton's method. This is now doing the RAM rule. So this is how you can evaluate and check if you're doing integrals correctly when you do the limit of the Riemann sum, is you can type them in the calculator to see, do you get the same thing? Now, as you look at the homework that's out of the book, these two problems, 31 and 32, you are to do like this on the calculator. So if you don't have a calculator that can do this well, you may want to borrow my one quick and do this in your calculator before you leave. Our limit of our Riemann sum works when we have nice x's, right? Polynomials we can easily multiply out. As our functions get harder, that's where this calculator will become useful. And 31 and 32 are like that. We wouldn't be able to do them with the limit of the Riemann sum because the algebra for us right now is too difficult. So that is the limit of Riemann sums as a definite integral.